Hello, this is the third of the matrix algebra videos that you need to watch to prepare for class. In the end of the second video, we defined a determinant. A determinant is a single value that represents a separate value that represents a square matrix. A singular matrix is one that contains linear dependency. And what linear dependency means is that one or more vectors of a matrix, either rows or columns, are a linear combination of the other vectors in that matrix. And you can see this down here, where if you look at these numbers, 3 and 1, if you multiply them by 2, so that's a linear dependency, you would get 6 and 2. So 3 times 2 is 6, 1 times 2 is 2. The determinant of a singular matrix will equal 0. So if we were to go through the steps and create the determinant of matrix B and multiply 3 times 2 and then subtract 6 times 1, the ultimate outcome here would be 0. And this is an important distinction to make because there are a lot of statistical procedures that require that you don't have any singular matrices, one of which is regression. So if you were to make data that had a singular or linear dependent, if one x variable was linearly dependent on a different predictor x variable, then you wouldn't actually be able to calculate your regression. And this can sometimes happen if you're making fake data, but sometimes it can happen if your just x variables are very strongly correlated with one another. So as a consequence, we need to be careful of this singular matrix. Where we're going to finish up for the last operation that you're going to learn is a matrix inverse. This is how, or essentially related to division using matrix algebra, where division matrix algebra is done by multiplying reciprocal. Remember that in geometry, what you could do if you wanted to, if B equaled C over A, the other way that you could write that is 1 over A multiplied by C, because any given term, A here, is equal to, or when divided, is also equal to 1 over A. So, for instance, if I were to write, 1 over A multiplied by C is also equal to C over A, which is essentially what I'm trying to get across. The reason that is important is because that's how we're going to do division when we divide two matrices amongst each other. The inverse of a matrix is noted with a -1 exponent, so the inverse of an A matrix is going to be denoted as A to the -1. If we know those steps that I just went through, that C equals A times B, and we wish to solve for B, what we do is would state that B equals C over A, just as what I was showing, or B can equal 1A times C. In matrix terms, we're going to write that as the B matrix equals the inverse of A times C. Note that the C matrix here, that should be matrix, I apologize for the typo, is pre-multiplied by the inverse of the A matrix and not post-multiplied. What I mean by that is that B equals A to the -1 times C. That would not be the same as B equals C times A to the -1, or the inverse of A. And that goes back to what we talked about earlier in the videos, where we said that multiplication in matrix algebra is associative, but it is not commutative. So when we calculate an inverse, it requires multiple steps. The first thing we're going to do is we're going to calculate the determinant of the matrix. So we've already learned how to calculate determinants. Then we're going to create an adjoint, which we have not done yet, so we'll go over how to calculate an adjoint. And then we're going to divide each element of the adjoint by the determinant, which is essentially identical to multiplying by the reciprocal of the determinant, which you'll see. So the first thing was to let's learn how to make an adjoint. When you make an adjoint of a 2 by 2 matrix, all you do is you're going to swap the elements of the principal diagonal, and you are going to make the off-diagonal elements negative. So instead of A, B, C, D, we're going to swap the principal diagonal, so the element 1, 1 is now D, element 2, 2 is A, and where the off diagonal are going to become negative. So C is negative and B is negative. They aren't swapped. They stay in the same place. They're just negative. So we've now created the adjoint of a matrix. The overall formula for calculating an inverse is we're going to do 1 over the determinant. And remember, the determinant is a single number. So essentially what we've done here is we've created a scalar, or a single value. 1 over the determinant of A, and we're going to multiply that by the adjoint of A. Well, the first thing we'd have to do, now that we have the adjoint, we still have to calculate the determinant. So remember, a determinant is when you multiply the principal diagonal and then you subtract the multiplication of the off diagonal. So I have 4 multiplied by 2, which is going to be 8, minus 3 multiplied by 7, which is going to be 21, and if I do 8 minus 21, I get negative 13 as the determinant of A. Next, we have the adjoint of A. So, as we created before, the adjoint, we flipped the points of, or the parts of the principal diagonal, 2 and 4 now, or 4 and 2 is now 2 and 4, and we've made the elements of the off diagonal negative, and we finish it off by multiplying the reciprocal of the adjoint by the elements of, or the reciprocal of the determinant by the adjoint. And since we're multiplying by a scalar, we multiply 1 over 13 by 2, and 1 over 13 by negative 7, and so on. And what you'll see that comes out to be is we'll have, in decimal format, negative 0.153, 0.538, 0.230, and 0.307. And that is the inverse of A. Now, just to introduce things, everything I've shown you up until this point has mostly been with 2 by 2 matrices, especially with an inverse. Once you get into a 3 by 3 matrix, it becomes much more difficult and tedious. The mathematics are just so many extra steps. So for now, I'm just going to illustrate those values for you, and when you do this, the 3 by 3 matrix for your homework, I actually provide an Excel program to do the math for you so that you don't have to do it by hand. So the determinant of a 3 by 3 matrix, if I just made the elements in letter format, A, B, C through I, and so on, where the determinant of remember, the determinant of a 2 by 2 matrix would have been, if I had equaled A, B, C, D, the determinant of a 2 by 2 matrix was A times D minus B times, sorry, that's a minus sign, minus B times C. So you can see how when we add in the extra elements for a 3 by 3, this becomes much more busy. We have A times EI minus FH. So you see how we have the principal diagonal going along right here. The elements of the principal diagonal, AEI. Right along there, and then we're going to work on the off diagonal. So E times I, F times H, and then for B, we multiply that by F times G and D times I, and then C, we're going to multiply that by D times H and E times G. There's a really clear mathematical steps to that, but it's not something you necessarily need to know for this class. Now, if you thought the determinant was hard, looking at the, you'll see how calculate the adjoint, it's even busier, where the adjoint for a 2 by 2 was just flipping, when we had a 2 by 2, A, B, C, D, the adjoint was, we flipped the principal diagonal, and then we made the off diagonal negative. You can see how for a 3 by 3 that's even more busy and hard or complex. So again, when you do a 3 by 3 matrix, you're going to have all those calculations. You can enter them into a program that that's been created in Excel, and your math becomes very easy. So that's the end of the videos to watch for class. take this information, practice it, feel comfortable with it. You'll be using these numbers in order to apply it to regression for your homework assignment. All right, thank you.